I'm going to talk about climate change, and I also want to talk about sustainability. And I'm going to take it beyond science and into really what I think is sort of the basics. I mean, what is our role here? What is our responsibility? So I think in the end, we can talk a lot about science, and you've heard a lot about that. We can talk a lot about economics, and these days all you hear is economics. But I think the part of the debate that we have not heard enough about is the moral and ethical part. You know, what is our responsibility here? What is right and what is wrong? Because I think in the end, economic arguments, while powerful, aren't as strong as arguments about what's right and what is wrong. And I'm not going to try to tell you what's right and what is wrong. What I'm going to do is try to arm you with information and then challenge you to think about that. That's what we do at the university. That's what you should do throughout your life. Challenge yourself. Don't be comfortable with your knowledge, but challenge yourself. So let's go down this road and see what happens here. I'm going to only try to make 3 points this evening, and I think in a good talk you shouldn't try to go beyond that, so I'll tell you what they are right up front. Why you should bother about climate change. Number one, because it's real, and we'll talk about that, and because it's actually really simple. So we hear a lot about complexity. We hear a lot about complex climate models. We hear a lot about how we possibly understand this huge complex Earth of ours. I'm going to try to get beyond that to the simple stuff. What do we really know? What do we know with high degree of certainty? That is, we know it, period. I shall back off. I'll try not to talk like a scientist again this evening. I'm not going to talk about high degree of certainty. What do we know and what can we rely on? Second, because there are real impacts, and we'll talk about some of those impacts. Some of the ones are obvious today. I'm a paleoclimatologist, so I look into the past. I use ice cores and other things to look into the past. And what I'm going to do is look into the past and tell you that we know we don't need complex climate models. We can just look at what the Earth tells us, and the Earth is going to tell us this is what I'm going to look like sometime down the road. Right, so what does that look like? And the third is, and this is probably the most important thing, it's a hard problem that will take many of us, matter of fact, all of us, to solve it. And it's hard for many reasons. From a university professor point of view, one of the hardest things is to get the physical sciences, social sciences, the ethicists, the humanists to talk to each other. We don't do that very well. But we'll talk about the other reasons, the political reasons, the policy reasons, all the other reasons why this is a tough problem. Okay, so first point, because it's real and it's actually really simple. So forget the complexity of the planet. Let's take a look at the globe. We're going to look at the entire planet in one piece here. Right? And if you look at the planet in one piece, it turns out that you really only need to know 3 things to know what the climate on the planet is. You need to know how much energy we get from the sun, because we are a sun-driven planet. 99.99 something % of the energy that we have on the surface of the Earth comes from the sun. Right? Very little comes dribbling up from below. Second, how much of that energy is reflected back to outer space? So on this planet of ours, you can't see it on here because it's a stylistic version of this, but in the wintertime, you know that there's a lot of snow out here. That snow is white. It reflects the incoming solar radiation, so the sun doesn't have a chance to warm the planet up. So the more reflectivity there is on the planet, the less energy we have and the colder our planet is. Right? And the third is the amount of greenhouse gases. Now, we've heard a lot about greenhouse gases, but greenhouse gases are a fundamental part of our climate system. These are gases that do not absorb the sun's incoming energy. What they absorb is the Earth's outgoing energy. Now, every molecule, every time you got 2 atoms together, like a CO2, which is a C with 2 O's on the side, or an N and an N, anytime you got 2 atoms together, they vibrate. That's just a fundamental principle of chemistry, fundamental principle of physics. So pretend I'm a CO2. I got a carbon in the middle, and my fists out here are oxygen, and I'm vibrating away. Here comes the sun's energy. I don't really care. Right? You've got to feed me the right frequency of energy to excite me, to get me to absorb that. I absorb infrared radiation, and the Earth emits infrared radiation. So do you, and so do you, and so do you. So do all of us in this room emit infrared radiation. But the Earth does. And so as this infrared radiation tries to leave the planet and go into outer space, because we can't accumulate energy on the planet. If you did, we'd just all burn up, so that doesn't happen. So as this energy tries to leave and go into outer space, it gets absorbed by carbon dioxide, water vapor, methane, nitrous oxide, these other gases that are in the atmosphere, and they absorb that energy and they accumulate a little bit of extra energy in the atmosphere. And energy in the atmosphere is the climate system. Our climate system is basically the distribution of energy on the planet. And about half of the energy that we feel or is reflected is in terms of heat, temperature. Right? So that's a big, big important part of our climate system is temperature. So these greenhouse gases are the third key part. You got more of those things, you're going to have a more energetic atmosphere, you're going to have a warmer planet. If you've got less of them, you got a cooler atmosphere, you have a less energetic planet. Okay? So, greenhouse gases, and this is important, are a natural part and a very important part of our climate system. Basically, without them, we don't have a habitable planet. So, you can take the temperature of the Earth in a number of ways, but one of the things we can do is we can go out to the top of the atmosphere and we can measure how much energy are we getting from the sun. In other words, how close are we? The closer we are to the sun, the warmer our planet is, the farther away we are from the sun, the colder our planet is. As it turns out, we're at a distance from the sun that would give us a temperature, an average temperature, of about negative 18 degrees Celsius. Frozen. That's a cold planet. Right? Too cold. Certainly too cold for advanced life. The Earth's actual temperature, though, we can go out there with thermometers and measure the temperature of the planet. And it turns out if we go out there with thermometers, the planet's temperature is about plus 15 degrees Celsius. I can convert these to Fahrenheit, but I would mess it up. So let's just go with Celsius. Now, this is actually quite a cozy planet because it's hot, but not too hot around the equator, and cold, but not ridiculously cold at the poles. And this is a very nice place to live. The difference between here and here is because of greenhouse gases. This is simple physics. Right? You can't stop molecules from absorbing energy any more than you can stop any other basic physics. I mean, there are certain laws we have to obey. Right? You all heard of the first law of thermodynamics and the second law of thermodynamics. These are laws you have to obey. You simply cannot pass a law against it. This is something, it's going to happen whether you like it or not. And this is something that happens whether you like it or not. And this is actually a very good thing. If it wasn't for water vapor, which is the #1 heavy lifter when it comes to greenhouse gases, and CO2, and methane, and nitrous oxide, these other molecules that just happen to vibrate with a frequency in infrared, we would not have a planet that would be habitable by creatures like us that require liquid water, that require the kind of sophisticated agricultural systems that we need in order to grow all the food we need and do all the things we need to do. So I grew up with the little adage in my head, the postman is your friend. I haven't a clue as to why that. They told me that when I was a kid, but that's what they told me. Greenhouse gases are your friends. Right? Without them, you don't have a habitable planet. All right, now, you can have too much, or you can have more of a good, let's say not too much, you can have more of a good thing. We are adding greenhouse gases to the atmosphere in a number of different ways. But what we know from what I just showed you, the simple physics of it is, if you add more greenhouse gases to the atmosphere, you will warm the planet up. You will change climate. Absolutely you will change climate because climate is a distribution of that energy. And as I said, about 50% of that energy is temperature. And so if you put more greenhouse gas in the atmosphere, you will raise the temperature of the planet. That is simple physics. And again, you cannot get out of that. I use an exercise, I've taught a course on energy in the environment for years and years and years. And I do a little exercise with my students. I have one of them come up and stand on a chair in front of the room. And I'm not going to ask you guys to do this. Right? But imagine somebody standing on a chair in front of the room here. Right? And then we go through this little exercise. What would happen if I pushed? Let's imagine my dear wife is standing up on this chair. What would happen if I pushed? And we talk about, oh, she would fall over and, well, you tell me. So if my dear wife is standing up on this chair. Yeah, go ahead, come here. Stand on the chair.
Yeah. I shouldn't have worn heels.
Yeah. So what happens if I push her this way?
She goes off balance.
Yeah, she go off balance, right. If I shove her hard enough? She goes over. Let's have fun with this. What if I tied her hands behind her back and shoved her forward? What would happen then? Might she break her nose? Break something else? Would I be in some serious trouble? Absolutely, my dear. Off you go. Vanna. Oh. Sorry, that's a bad joke. I'll pay for that later, right? In all the years that I've done that little exercise, including tonight, no one has said to me, she won't fall.
She'd push back.
Of course she'd push back. Will she fall? Of course she'll fall. And why? Because gravity. And because we know deep down inside that regardless of what we think, gravity is going to happen, right? The same thing is true with greenhouse gases. The same thing is true with all the other simple physical principles that we live with day in and day out. We simply can't ignore them. We can't pass a law against them. It's not a question of belief. You don't believe in whether or not greenhouse gases absorb energy. That's going to happen whether you believe in it or not. This is a simple physical principle, just like gravity is a simple physical principle. All right? So if we put a lot of these things in the atmosphere, we're going to have some sort of climate change. At this point, we'll have all the arguments you want. Whether or not it's going to get warmer in Colorado, colder in Colorado, more snow in Colorado, less snow in Colorado, what the exact reflection of that is, whether or not the U.S. does better than Canada, or whether or not Russia does better than the U.S., all of those things that we argue about, that requires some sophisticated modeling, and we can have those arguments. But you simply cannot argue about the fact that if you put a lot of greenhouse gas in the atmosphere, you are going to change climate. Okay? All right, off we go. So, number two, second point, important point here of the evening. There are real impacts. Our planet is warming up. I'll show you that slide in a second. But there's a lot of other things that are happening. Arctic sea ice is shrinking. And if you want to learn more about this, the group on the planet that tracks Arctic sea ice and reports on it is the National Snow and Ice Data Center at the University of Colorado Boulder, and you can go to their website and learn all sorts of things about sea ice. Now, why is sea ice important? Remember the number two reason why climate changes. Number one was the amount of sun you get. Number two was the amount of reflectivity there is on the planet. And when you replace white ice with blue ocean, you greatly change the reflectivity. And we are today seeing some very interesting climate changes occurring on our planet as sea ice shrinks, particularly in the summertime. Right? For example, we have seen, as the Arctic warms up, the temperature difference between the Arctic and the rest of the globe goes down. As that goes down, the jet stream, how many people, watch the weather in the evening, you heard about the jet stream, the river of air. I just came from a meeting with a bunch of TV meteorologists. That was my best TV meteorologist voice here. Anyway, the jet stream, as it circulates around, it gets slower and lazier because it's driven by the temperature difference between cold and warm. So as it gets slower and lazier, it gets bigger loops. And bigger loops mean that storms go more slowly. And what we've seen in the last few years is some very interesting situation where in the wintertime, we get cold air coming down because cold air is not bottled up anymore. And we get storms that go slower and slower, and they dump more snow and they dump more rain. And this is a very natural consequence of something like this happening. As sea ice shrinks, as you decrease the reflectivity, as you warm up the Arctic, you start to get these kind of changes. Counterintuitive, if you will, in that the cold air shrinks out, or slinks out, I shouldn't say shrinks out, slinks out. But indeed, that's the kind of interesting surprises that we are going to have to come to expect as we go through climate changes. So this is a movie of, and what they've done here is they've tagged every point, and if ice hangs around for more than a year, it gets thicker, and it gets whiter. So they tag them as white. So what you see here is the Arctic circulates, ice flows out around Greenland here. This is what sunk the Titanic. And so these are basically chunks of ice that come out. And what you're seeing here is an increase in blue. Blue is 1-year-old ice, right? The stuff up here. And what's happening is the old ice is being shoved out and it's not being reformed as time goes by because it's not cold enough to reform ice and to keep ice around here for several years. Now, ice that's only a year old behaves differently than ice that's thick. Ice that's only a year old can be eroded very rapidly. As an example, the Great Lakes of the U.S. used to freeze over every winter. Lake Erie, Lake Superior, etc. These are pretty big places, right? They would freeze over and then melt out in the spring. Now, for those of you who remember this, how rapidly can something like Lake Erie melt out? How long does it take to go from an ice-covered lake to no ice on this lake? It takes a couple of weeks. You can look it up. We have the data, the observations there. It only takes a couple of weeks because ice that becomes that thin is attacked from the atmosphere by warming and attacked from the lake by warming, and then the wind gets into it and you start to stir it around, and just like you take a cocktail with some ice cubes in it and you shake it around enough, you can melt that ice more quickly. That's what happens in Lake Erie. That's what happens in the Arctic as well. So once you start to get this situation, then you have something we call that has a tipping point to it. So this, in the summertime, can lose a lot of its ice in a hurry. And what we're seeing more and more often is in the summertime, we lose a large chunk of this ice. The ice melts back into here. We now have shipping going across the Russian Arctic. We occasionally have ships that take a more daring route because, as you can see, the ice tends to pile up down here. So the Arctic is changing. Our Navy is well aware of this. Our Navy is concerned about what to do about this. We have oil companies that are buying very large and expensive icebreakers because this is one of the last frontiers for oil. So it's changing. What else is happening out there? It's getting warmer. You can measure this. This is NASA, the Meteorological Office at the famous Climate Research Unit. We can talk about them if you want. NOAA and the Japanese Meteorological Agency. There are different ways to collect temperature measurements around the planet. And you can see that they don't all agree all the time. But in general, everybody's got the planet warming up. And the planet is indeed warming up. One of the things that happens when the planet warms up is its sea level rises. And this is another one of those simple physics things. These are tide gauges going back to the 1880s, and there's a whole bunch of them on the slide. Satellites start to come in up here. It's actually not, measuring sea level is not an easy thing to do because sea level changes. Sea level may be level, but it's not level. And so sea level is higher in some spots and lower in other spots. So actually measuring this is not an easy thing to do. Plus it tends to go up and down, obviously, as the moon and Jupiter and other planets tug on water. But the trend is upward over the same period that the planet was warming. Now this turns out to be relatively straightforward. When our planet warms, sea level rises. When it cools, sea level drops. And there's two very simple physical reasons for this. One is when you warm up water, it expands. All right. And the second is, as you warm up the air, land ice melts. And as land ice melts, it goes into the ocean. Okay. And there's also this powerful albedo feedback, this reflectivity feedback, pardon the word here. There's a big reflectivity feedback. As you lose the land ice, you lose the white bits. The planet gets even warmer, so there's an actual feedback that goes on there. So sea level and temperature turns out to be one of the most robust relationships that we see on the planet. You can plot estimates of the temperature of the planet versus estimates of sea level, and I'll show you in a minute. You get a very good relationship. When we're warmer, higher sea level. When we're colder, lower sea level. One of the ways that our life is easier from a paleoclimate point of view in determining this relationship is that the sea level changes are not small. During about 20,000 years ago, when glaciers covered most of Canada, Fennoscandinavia, the hockey season was much shorter because none of the Canadian teams could play. It's a joke, folks. Come on, work with me here, huh? Come on. Where was I going with that? Oh, yeah. Sea level was about 300 feet lower than today. Sea level has been 50, 60, 70, 80 feet higher. So sea level is very dynamic. And the range of dynamic variability is large. So when we go to look for, matter of fact, you can see old beach terraces that are well inland today in the Carolinas, in the South, places like that. Along the West Coast is more problematic because it's going up and down because of plate tectonics. But in areas that are pretty stable plate tectonically speaking, you see these beach horizons, and they're good 30, 40, 50 feet above where sea level is today. And they're very easy to spot, and you can very easily identify them as beach horizons. So we know that this happens. This is just a slide showing you from the present going back 400,000 years. Our climate goes through cold phases and warm phases, as you see here. And these are sea level estimates that we can place on those that have been dated by various mechanisms. The last time the Earth was as warm as it is today was about 120,000, 130,000 years ago, and sea level was about 5 to 8 meters higher than it is today. 5 to 8 meters, 15, 20, 30, 25 feet, something like that. About 2 meters higher, we think about the same. And in some of these, this happens to be a warm period that lasted a long time. And during that long-lasting warm period, sea level got to be 20 meters higher than today. So more than 60 feet higher than today. So sea level may be level, but it's a very dynamic thing. And this is something that we don't really, this is not something that's in our collective memory. Right? We populated the planet primarily by ship. So most of our major cities are along coasts. And sea level has been fairly level for the last 13,000 years or so, which is a time period in which human beings have spread out all over the planet. So the concept of the sea level going up and down is not something that is in our cultural memory. Right? You got to go further back in time in order to see it, but it's a very real phenomenon. So what does this look like? So by the end of this century, a very, very good bet is that sea level will be about 3 feet higher than today. Right? And that's based on a number of studies, and it's a very, I wouldn't say it's very conservative, it's definitely a conservative number. Right? What does 3 feet of sea level rise, or about 1 meter, look like? This is Miami with 1 meter of sea level rise. I spoke to the television audience in Miami a couple of weeks ago and basically told them that their city was toast. We didn't do anything about it. I don't think it was terribly well received, but here's the airport out here. Miami has a little bit of ridge here. Miami Beach is all underwater here. But this is a non-functioning city. And it's non-functioning for a variety of reasons. The gas lines that run underground are no longer functioning because there's saltwater intrusion coming in here. If there's any buried electrical lines, forget about it. My favorite is, toilets work on the fundamental principle of gravity. Right? You flush and it goes downhill. Well, if the bottom of the downhill is rising on you, then things don't work so well. So there's a whole bunch of things that are fundamental to a city that aren't functioning so well anymore. Now, it's also important to recognize that scientists like to pick these things like by 2100 this will happen, and by helpful in terms of getting you to see where we're going. But I think it's also a little bit of misleading because it's not going to stop there. Sea level will continue to rise. 3 feet is not the end of the story. It's just going to continue to go up. And one of the interesting questions that I work on today is how high is this going to go? All right? So let's ask that question. Well, okay. I had to throw this slide in. Think about it. Miami has really no future much beyond this century. Miami as a city started about 100 years ago. So Miami will get about 200 years worth of Miami-ness. There's actually a very nice book. Says, I read this recently, a book. The title is Miami, City of the Future. So. Okay, so this is some of the types of data that we produce. This is a plot of global mean temperature, estimated by a whole variety of ways, and sea level, primarily estimated by looking for these beach horizons and then measuring how high or low you are below sea level. And what you see here is a pretty good relationship. During the last glacial maximum, about 20,000 years ago, sea level was down here. This is about 100 feet, 100 meters, so about 300 feet below where it is today. The last interglacial period I showed you on that plot is right here. Period we're going to talk about in a minute called the Pliocene, which is about 3 million years ago, lies around here. And the Eocene, if you go back far enough in time, about 40 million years ago, there was no Antarctica and there was no Greenland. They were land masses without ice on them. The Earth was warmer. CO2 levels were much higher, and all of the land ice had melted off. And so you get about 70 meters, 70 to 80 meters of sea level rise. And that's about as high as it can go without adding more water to the planet or rearranging the continental configuration. This is the forecast that we keep reading about in the newspapers for the year 2100. Right? And the point's correct. It's not predicting no sea level rise. It's just that it's so close to, the scale is so big that this point is just barely above this line. Now you can see that, indeed, from a paleoclimate point of view, if this is the kind of warming we're going to get, eventually the Earth wants to take us up into here somewhere. And that's what's going to happen. I mean, we don't, from a climatological point of view, we can't see any way around that. Again, the physics are too simple. If this was a very complicated system with a lot of feedbacks and a lot of equations that we didn't really understand, that'd be one thing. But no, I mean, basically, as you warm the planet up, water expands and ice melts. And so this point's going to crawl up to here. It's really a question of how long it takes to get up there. So let's take a look at this. So let's, go back and ask the question, what did the planet look like the last time we had this much greenhouse gas? You got to go back about 3 million years. That's when we had roughly 350 to 400 parts per million CO2. Today we're at about 390. So keep your eye on the paper. When we hit 400, we ought to at least, have some sort of celebration of some kind. The planet was significantly warmer. It was warm enough that there are trees growing at the top of the Arctic Circle. Those trees are still there. We can dig them up. Right? When the planet got colder, things quit rotting up there, and there's actually tree trunks you can still find up there. There was certainly less land ice, certainly less sea ice, and sea level was about 20 to 25 meters higher than today. So 60-something feet higher than today. That's with today's level of CO2 in the atmosphere. It's really only a question of how long it takes to get there. And we'll talk a little bit more about that if I speed up here. I need to speed up a little bit. Because we live on a water planet and it takes water a while to absorb heat energy, I think we all know that, a watch pot never boils, you've heard that before. It takes a while for the planet to catch up with the climate changes that we have imposed on it. So it may be hundreds of years before we reach these kind of levels of sea level, but there's no reason to think we won't get there eventually. Now, what does 20 to 25 meters of sea level look like? You can make all sorts of wonderful plots. Google is a wonderful thing. This one is just one of my favorites. And you got to have fun with stuff like this. If you get depressed about it, you're missing the point. This is Delaware, which I kind of like this because what was the first state in the Union? Delaware. So first in, first out. All right, so Delaware's gone. So we'll be down to 49 at some point here. Typically, I show a picture of Florida. Florida is I don't have one, but I'll tell you about it. So Florida is an island down in the Orlando area, and the rest of it's pretty much covered with water at that point. So what's down in the Orlando area? Disneyland. Disneyland, right. So at this point, I challenge my students, what conclusions can you draw about climate change? And they invariably come to the correct conclusion that climate change is a Disney plot, right? Because Disney's going to have its own private island, going to sail the princess right up to to Disneyland, and off you go. So that was another joke. Don't turn me into the Disney people. They scare me. This is Bangladesh. I just had to show you this because the borders of Bangladesh is like somebody said, all right, we're going to pick this, the 60-foot sea level contour, and we'll plop up country in there and see what happens. In seriousness, this creates a lot of refugees, creates a lot of climate refugees. And our Pentagon, if you read their reports, they talk about this. They're worried, they're concerned about what happens as low-lying areas flood. What does this do to the stability of nations? And what does this do? What is the Army and the Navy and the Air Force, what do they have to do to be prepared to deal with these sorts of things? Okay. So, third point, it's a hard problem. It will take many of us to solve it. Why is it hard? It's political. If you say the words climate change, think about it. Two simple words. Climate, easy word. Word we like, word we use all the time. Change, we use that word all the time. You put the two together, and you get friction. And you get visions in your head of conservatives and liberals. You get visions of your head of talk show hosts. You get all sorts of stuff popping in there. That's what's happened to the term. And it's happened for a very good reason, because it's political. We can't stop things in our society from being political. We have a very open society, and thank goodness we do. But this is the reality of what happens when this is sort of, the ups and the downs of having an open society. And I wouldn't change it at all. Second, there's a lot of money at stake. Right? If we got a bill every year for energy in the US, it would be about $1.4 trillion per year. That's what we pay for coal, oil, natural gas, and the small amounts of renewables that we have out there. That's a lot of money. Is it all about money? Again, think about this. Maybe $1.4 trillion generates a lot of money for lobbyists and all the other things that we, in our society, that are part and parcel of how we do business, right? So it's not a surprise to me, it shouldn't be a surprise to you, that a subject like this involves a lot of people, and involves a lot of discussion, and involves a lot of lobbyists, and involves all this other stuff, because there's a great deal of money at stake. It's an easy thing to see. The impacts come after the causes by about 50 years, again because we live on a water planet. It takes a while for the ocean to heat up. So what we do, what our generation does to the planet, our kids get to deal with. And what they do to the planet, our grandkids get to deal with, et cetera, et cetera. This 50 years is a pretty nasty time frame, right? If you think about it. Very difficult politically to deal with anything on a 50-year time scale. Very difficult to deal. Basically, this is an intergenerational issue. And if you ask people what's important, people will tell you, I'll list, this, this, and this, and this, but, kids and grandkids are frequently left on their own when people rank priorities. So if cause and effect are not immediate, it's really hard to provoke action, and that's a reality. Why is it hard? The problem is global, so it's an international challenge, right? And I'll talk more about global here in just a second. But to me, climate change is really a part of a larger issue that in dealing with population, and dealing with food, in dealing with clean water, in dealing with enough mineral resources, all the other. Energy is just one of those resources that we take out of the ground and use. There are all sorts of other resources. And the real problem here is sustainability. So why do I say that climate change is training wheels for sustainability? Well, if we can figure out climate change, that means that we figured out how to get along, at least have a treaty that works, globally speaking. Right now, we're a bunch of nations that carve up the globe, and we really don't get along at all. Right? And we can't get China and India to do anything, and they can't get us to do anything. And as long as we're not doing anything, then we keep burning fossil fuels and these CO2 and other things go in the atmosphere. So if we can figure this out, if we can learn how to address this global problem, perhaps we can tackle others. So I actually have some faith on this one. The problem is global and the world is changing. This is a plot of, this is from your Energy Information Agency, your Department of Energy. This is a plot of the United States energy use. Here's 2008 on here, India and China. And you see, for example, China now produces more greenhouse gas. They use more energy than we do. This is in total energy consumption. They will use about twice as much as we do by 2035. Right? So the problem is out of our hands, if you will. And the fifth reason why it's hard, there's a whole bunch of these. Because grow is what we do. If you think about it, that's really burned into our psyche. We've got to grow. We've got to grow the economy. We've got to grow this. We've got to grow that. Now, I don't have any answers to what happens if you don't grow. Right? But clearly, if you continue, this is now CO2 emissions. If you continue to grow, you continue to, and you use fossil fuels, you'll continue to produce carbon dioxide and put that in the atmosphere. And grow is important because here we are in 2010 in the midst of still a global, at least economic downturn, if not out-and-out recession. And there are parts of the world like China, India, et cetera, that are really ramping up. So we burned more fossil fuels last year than we have ever on the planet. In the midst of an economic downturn, we burned more fossil fuels than we ever have on the planet. And we do that despite whatever comes our way. This is the CO2 emissions showing oil crisis back in the 70s when OPEC came into business. Slowed us down, didn't stop us. U.S. savings and loan crisis, actually was more hurtful, slowed us down, didn't stop us. Collapse of the former Soviet Union. This is not Florida State University, which is where I got my degree. It has not collapsed. Asian financial crisis, and this is the global financial crisis. So we're good at continuing to use energy. And this is all energy use. This is coal, oil, and natural gas. Continuing to use it really doesn't slow us down very much. Okay, it's not just about energy. We talked about CO2. We hear about it all the time. I'm going to tell you, it's not your biggest problem in the long run. The biggest problem in the long run are gases like methane and nitrous oxide, which are food gases. You can deal with energy. You're going to run out of oil, and you're going to run out of coal even, and we'll run out of it faster than you think we will. But you're going to have to continue to eat. You're going to have to continue to fertilize, and this stuff comes from excess or even fertilizing, period. So you fertilize, you're going to produce more nitrous oxide. You grow rice, you're going to make methane. You got cows, you're going to grow methane. You're going to make methane. You're going to eat, you're going to make greenhouse gases. So we have to come to grips with the fact that we have a footprint on this planet, and we're going to have a footprint on this planet. We're going to change climate. Whether we deal with energy issues or not, we're going to change climate. So this is one of those, you're going to have to learn how to adapt points. So is it surprising that human beings are causing climate change? No, not really. I've got a whole bunch of these, but we'll do some short ones here. Well, I talked about the first one. If you add up all the dirt that flows in all the rivers and streams and blows through the atmosphere every year, and this is actually a relatively easy thing to add up, we move 10 times more dirt every year with our tractors, and not with our tractors, with those Caterpillar gizmos and backhoes and stuff like that, than nature does. 10 times more every year. All right? One of the fundamental principles of our planet is that bacteria take nitrogen out of the atmosphere and make ammonia and nitrate as a byproduct. That ammonia and nitrate is needed by plants. Plants take carbon dioxide and sunlight and water, and they make sugars, and that is our food source. Our species, all animals basically, rely on those plants, rely on photosynthesis to make the basic sugars that makes the whole thing work. And without the bacteria, you don't get the sugars. You don't have the plants. So ask the question, can we make fertilizer? Yes, we can. We can take nitrogen out of the atmosphere, figured out how to do it in the 1930s. We can convert it to ammonia and nitrate. We sell it at Home Depot. Today, short time later, we make as much fertilizer, nitrogen fertilizer, as all the bacteria on the planet. I agree. I can go into other examples here. I teach a course on energy and environment, so one we're talking about right now is our current energy needs equal pretty much all the harvestable wind energy in the lower atmosphere on land. So in other words, if we were to try to run our global energy on wind energy, you have to carpet land surfaces to generate that amount of electricity. So there's a huge amount of energy use that we have out there. Now, how is this possible? The power of the exponential. This is the planet from outer space. This is what you would see if you were cruising along if you're an alien. That next talk, all about the aliens out there, right? So I knew we'd loop back to this. This is what you see. You know that there's somebody on this planet, and you know they're big, right? This is basically Nikon photographs of the planet where they take out the ones with clouds and substitute ones that don't have clouds and put the whole thing together. And this is what we look like at night. So we produce a lot of light. Almost all that, 90%, is fossil fuels. So we're big. I mean, I've been trying to convince you we're big on the planet. We're big. Hopefully you're convinced. I have my students print this out and put it on the wall and stare at it for an entire semester. And I think they eventually get it. So the power of the exponential. Population. We all know that population is going up, right? And we live in that very interesting time when we've gone from basically the 1800s here, when we first passed 1 billion, to about 200 years later, we're at 7, 8 billion. So all exponentials go through a period of explosive growth. And all populations do as well. And we're beginning to slow down. But at 7 billion people, there's a lot of us on the planet. This is a problem. We can't really service 7 billion people. We don't have the calories for food, the fresh water, the energy resources, all the other things we need. This is a problem, and we'll have to deal with that at some point. But we'll talk about that. The bigger problem, actually, turns out to be wealth, or not really wealth, use of materials. So in industrialized societies, we need a certain amount of energy, we need a certain amount of water, we need a certain amount of all these things. As it turns out, only about 2 billion of the Earth's 7 billion are utilizing lots of materials. About 3 billion people go out and collect firewood every day, and that's how they heat their home, and that's how they cook their food. So about 3 billion aren't even participating in this. Now look here, forget the US, here's China and India down here. On a per capita basis, China, which is past the US, still uses something in the neighborhood of 4 to 5 times less energy per capita than we do here in the United States. And the reason for that is because there's a lot of Chinese, right? There's 3, 4 times more. So they can have a middle class or an industrialized class that is roughly equal to us and still have a whole chunk of population that's not engaged in that. Now, what if the rest of those Chinese notice that their friends and neighbors are doing pretty well and they want to join in on the economic benefits, and they will want to do that? And so will the people in India, and so will the people in Indonesia, and so will the people in Brazil, and they're going to move up to here. And this is not a question of 10, 20% increase in energy, folks. This is going up 800%, 500%, 400% in terms of the amount of energy you need, in terms of the amount of water, in terms of the amount of food. This is the ultimate challenge of sustainability. How do you service that many people? And it leads to what I call the nasty dilemma. We would love others to live well. I've yet to find, I've given this particular slide a number of times, I've yet to find somebody who says, you know what, I don't want those folks in China or India or anywhere to have the lifestyle we have, because if they do, it's a problem, right? How many people would go with that one? Good. Right. Well, we got one over here. Way to go, Jane. Okay, so scientists knew this was coming decades ago. We said so. But the world has done little about it. For example, more than 20% of all fossil fuels ever burned were burned after 1997. So that exponential is very powerful. So you don't have to go, all of us can remember 1997, I think. What happened? Scientists failed to effectively communicate the problem. I think scientists have to take it on the chin on that one. Right? We knew what was going on, and we should have said, boy, you know, if you don't do something about this, you're going to be in big trouble. And we did not communicate that effectively. So that's what I'm doing here, trying to do that. Let me get up on the soapbox a little bit here. Part of the what I find distressing, if you will, about the fact that scientists failed to effectively communicate falls on the scientists. Part is on the way that we communicate information to the public. It's the media and all the other bits and pieces that are in there. But also it's the value of science. And I think one of the things that bothers me the most, and I rarely show this slide, but I'm going to get up on a soapbox here, I think the value of science in our society is being undermined. I heard one of the candidates for president, I won't say who, say, and I can't quote, but I'll get close, say that if he had to choose between the economy and science, he would choose the economy. And I just had to pause for a moment. You can't choose between the economy and science. That's like choosing between the economy and gravity. You can't do that. I mean, it's such a, this is where I think we're really suffering a little bit here. There's some good, solid information out there. It's not being fed into policy. It's not being fed into the decision-making process. Also, I think the value of education, and as an educator, I'm going to pound on this one. The value of an education and an educated electorate, I think this is also being threatened by the same process. So, we can come back to that. You can yell at me for that. I'll yell right back. Okay, so why bother? We have to. I think it is our responsibility. Right? We're the ones making the change. Now, you can sit back and just let this change happen. Your fellow Miamians will have to move. There's a whole bunch of things that will have to happen. But we need to take responsibility for this. We need to grow up as a species and deal with the impacts that we have. We can't just keep saying they don't exist. We can't keep saying it's not happening. We need to take responsibility. I've got a 17-year-old daughter, and she does not like that word. Neither do we. As adults, we don't like that word. But this is a word we've got to accept and a word we've got to deal with. And as I said before, climate change is only one piece of the sustainability challenge. So I want to end on a positive note. Right? I only have 3 simple rules for sustainability. First, everything must cycle. This is very simple. If you take something out of the ground, if you take bauxite out of the ground, you make aluminum, you got to keep cycling that around, or else you're going to run out of bauxite eventually. Right? Maybe you won't run out of beach sand, but you will run out of bauxite. Just recently, the Chinese yanked the Japanese on the end of a chain like a dog by saying, I'm not going to sell you rare earth elements that you need to make computer chips. Right? So that's another thing. If we don't cycle those sorts of things, we run out of things that we need. Right? So everything must cycle in order to really have a sustainable plan. Second, population must be controlled and vary inversely with resource use per capita. The more people you have, the less you can have living high on the hog. The fewer people you have, the more higher on the hog we can all live. Now, how do you control population? This is good news number one. It turns out that if men treat women better, population is controlled. Right? If women have value in a society beyond having babies, then you see population come down. And we see that in modern society, even in a society like ours, where our birth rates are not high because women are more valued. But think about it. How many women presidents have we had? All right. How many women are there in Congress? How many women senators do we have? We still got a long way to go to reach that equality point. But then you look at around the world. You look at Africa, you look at third world countries. The value of women is nothing more in many of those societies than having babies. And they have birth rates of 5, 6, 7 children per woman. That's where the population growth is occurring today. So one of the good news is, good news number one, if we simply treat each other a little bit better between men and women, we start to deal with that problem. And equality must be considered and acted upon. You cannot have very, very wealthy and very, very poor for the simple reason that on the planet, the very, very poor aren't going to care about the environment. They're going to go out and chop down all the trees because that's what they need to do to survive. Right? They're all going to become Somali pirates eventually because what else is there to do? Right? You cannot have a situation where some people are not participating at all in the economic benefits of the planet because they will prey on everybody and they won't care what the environment does. So that's good news number two. If we simply, again, if we got along a little bit better on this planet, some of the things, many of the things that we need to do to reach a sustainable society actually gets done. And I don't see any reason for not.